Okay, Assalamualaikum and a very good morning and good afternoon to everyone. Today is the second day of this continuation workshop on um, international online workshop on image processing using MATLAB with the topic on image transform and image manipulation. Okay, so we have Dr. Taha with us. We'll continue about the topic yesterday. So thank you for joining for today's session as well. So I hope this workshop will um, benefit in terms of your research to you. So we'll pass the session to Dr. Taha.
Thank you very much, Doctor. Thanks for all participants in this workshop. First of all, I want to ask if any of you wasn't here or didn't attend yesterday so that we can make a quick revision about what we studied yesterday. If you can write in the comment if you were exist or not yesterday. If not, please just write for the first time or the first lecture or first workshop day. So that we can just make a revision about what we get yesterday. So I'm going to go through the next day slides. According to our agenda, we are going to write to start with how we applied the lifting wavelet transform. We want to apply this lifting wavelet transform in image tamper detection and recovery. The goal of this workshop is how to find changes in images and alterations, and to figure them out, to specify them, and also to recover the image from that. So let me just share my slides. I'm going to start with a quick revision about what we said yesterday, and then we are going to continue. Doctor, are you seeing the slide now? It's clear? Okay. I think Dr. Rosetta left the meeting for some reason, maybe disconnection.
Yeah. Sorry, I got disconnected.
Okay, Doctor. But now you see, are you seeing my slides now?
Yes, it's okay now.
Okay. So I'm just going to make a quick revision about yesterday. We said that we have a wide distribution of digital images. We said that we are having millions of photos are shared every day, if not billions. So the question was, if we have about the statistics that 3.2 billion image per day. So can we tell which one is the original one and which one is the fake one? Of course, it will be difficult. It's not easy to find that out. This is the idea. Yeah, I think I got disconnected. Now it's the slides back, Doctor, right?
Not yet. Okay.
Okay. So the question was if these videos are and images that we can tell which one fake or not. So of course we need an automated algorithms that detect these changes, and also in the same time it will recover the changes in images. So yesterday we talked about the digital images. We talked about the type of them. We apply some of them in MATLAB. And also we applied lifting wavelet transform, which is to transfer the image from time domain to frequency domain to get some properties of that image. And we use mathematical representation for that. As a quick review, the pixel, we said that it is the smallest pixel element, the smallest element in the image. And each pixel can be one of three types, the general types: the colored image, grayscale images, or binary images. In colored images, each pixel is represented by 3 pixels, by 3 values. Each value is one color, for example, the red, green, and blue. And the range between the mixture between the 3 colors and the range of each one will decide what color that we have. And also for grayscale image, the second one here, is the grayscale that's used to specify one color between white and black. If it is 0, it will be white. If it's 255, it's will be 0, it's black, sorry, and 255 is the white. So between the two, we have the grayscale images in that. And also we have the binary images, which is either black or white. And we applied some image, how to read the image in MATLAB, and we displayed them, and we said that in MATLAB we can read the value of each pixel in the image after we apply image read. And image show will show us the image, and we can specify and we can read each pixel value and alter that value. For example, if we are going to have like this example, we get the image as a grayscale, and then we are, if it's more than 128, we consider this as just 1, and if it is less than 128, we consider 0. So we convert this image to black and white from a grayscale, as we see in this example. We apply some image geometric operations. For example, image rotate is using to rotate the image by single MATLAB command, and also we apply the image adjustment to enhance the brightness and contrast of the image. And we talk about how the importance of image compression if you don't need to have big images or high resolution images. So we can just, for example, in this example here that we see, both images appear similar to us in our presentation, but the first one is 4 megabyte, but the second one is 355 kilobyte. So by using simple commands, we can have better size for our system. Also, we talk about image encryption. If you want to send the image, we want to make it in a secret way, so we can create an algorithm that's used to change the locations and the index of the pixels. At the end, we are not going to send the image as it is. We are going to send it as an encrypted message, so that it will not be read by anyone unless they have the key or the algorithm that we use for that encryption. And we talk also, we have the age detection, which is used to separate images from or certain boundaries, as we said that we are using now in Google Meet. For example, we have the boundaries of the presenter that's going to be extracted, and then whatever there inside the background, it can be changed to any image. So using age detection, it can be used for that reason. And for lifting wavelet transfer and time domain and transform domain, we said that the advantage of it is to find some specifications in the image. For example, here in the, for this, we have, if we have in the details band, we can see that if we have edges or sharp changes in image between the background, which is the sky, and the mountain surface, we can have it clearly in this place in the image. So we can take this advantage of this by using a lot of things that, as one of them is they use the approximation band, which is this one, which is an abbreviated version of the image in a smaller size. We want to take it and use it to be the reference if any tamper happened to the image, as we are going to see in the example. Here we talked about the lifting wavelet transform. We said that it has some equations. The first one is to first to split the image into binary to even and odd position of pixels, and then we go to the predict step, which is that we're going to create for us the details band, and finally we go to the update, which is going to create us the approximation band. If you miss any of this lecture, we can share. We are going to share the slides again, so that we can you can read them and see that. This is a mathematical example that how to apply the lifting wave transform in mathematics, and we are going to solve it and the end by this slides. For today, we are going to take advantage of this lifting wave transform, but all you need to know, you can start from now if you didn't attend yesterday, but what the idea that we have divided the image into 4 bands, which is the details band and approximation band. The approximation band is an abbreviated version of the image that's going to be distributed inside the image so that we can recover the tamper. So image tamper detection and recovery. Now we are going to start with our new day slides. What we have here, the idea of image tamper detection is if we have any alteration in the image, we can detect this alteration, and then in the same time we are going to get it out. For example, if I have this original image, just have some pointer options, and I have the tampered one and I have the recovered one. So if you see that in this image, we try to hide the face, but using image recovery, we could return it back here in a pretty way that can show the face of that image. How we apply this, we are going to have some algorithm that we proposed in recent paper that's sent to Paris conference, engineering conference in March. We are going to explain it with the code to see how we can apply this. Before I write this, let me just make a draw for this. Let me just have a new slide, which is just an empty one. What we want to do, I will have the original image like that. And then we are going to apply the lifting wave transform as we said. Lifting wave transform would divide, as we said, the image into 4 bands. The band here is the approximation band, which has the same property of the image, but in less size. However, we're not going to use this the same. We are going to apply the lifting wave transform again on this one. So we are going to get this part of the image, which is approximation band, which has the important features of the image in a size which is quarter than the size of the original one. After I get this, I'm going to hide this part, which is the abbreviated view of that image, into the original one. And I'm going to distribute it to all pixels of this image, so that if anybody tried to cut or alter a certain part, other parts will defend, as we can see, and retrieve the original image as it is. This is the idea, is to take a part of the image, a small one that has the properties of the image, and then hiding them inside that the original one. How it's going to be applied? I'm going to explain the flowchart in general, and then we are going to go for details for one after one. The first part that we have here is to read the image. As we said that we can read the image in MATLAB using a command called image read. And then apply 2 LWT decompositions. 2 LWT decompositions are used to get the bands, for example, from approximation band, as we said, we are going to the original image divided into lifting wave transform for the first place, and then we applied it again, as we mentioned yesterday. So we are going to get this one, which is called SS2 in our example, because we said that the original image, when it's divided in the first place, it's going to be S for approximation and details. And then we are going to divide the S into S1 and D1. And this one is going to be divided into S2 and D2. This is after applying the LWT. Now we apply this again on lifting wave transform, so we can get SS2 and SS3, for example, and DD2, DD3 up to the names that we want to name. So after we get this one, which is the SS2, which is the small abbreviation part of the image, the important one that we have, we want to hide it. But how to hide this part? As you know, the image pixels, it's in SS2 also it's a number. For example, 128, 123, 124, it's a number. And if I want to hide it inside another number of the pixel, I mean inside the original one, of course it will have a big effect on the pixel. If it's, for example, 128, I cannot hide another 128 inside it or another 200 inside it, because that it will be a big change of the image. And also the size, if we are fixed on the 8 bits, it will not be enough. According to that, what we need to do, we need to divide or slice that SS2, the small portion, this one, to bit planes. What we mean by bit planes, that each pixel, which has 8 bits, we are going to divide it into 8 bits, and we are going to hide just one bit of that pixel, not all of it, just one bit. If it's one bit, it's either, for example, 1 or -1. If we are going to hide it in the original image, it will not be a big problem, because if I change a pixel from, let's say, 169 to 170, the human vision system cannot perceive that noise. As we are going to see in that, maybe if you have time at the end, to talk about how the human eye can interact with this, and how it can when it can see the noise and when it cannot. So I'm going to after that we are going to extract the bit planes of the approximation band, and then we go to the original image and find the average of each two pixels, and put the value in between. We change the value of the pixel to the average of its two neighbors, and then we either add one or subtract one from that average. If the pixel was 1 in the original, in the binary, we are going to add 1. If it was 0, we just subtract 1. And then save the image, and we are going to have a copy of the approximation band in all image contents. Let's go into details in the next part. I'm going to leave now how to retrieve the image after we explain the steps of the distribution, and then we are going to get the how to return the image. So in general, we have the following steps. Lifting wave transform, apply it. Then we are going to apply the binary planes. Then we are going to distribute the binary planes, which is the approximation band. And then in the recovery, we are going to extract the original image. So first, lifting wave transform, as we said, that we are going to apply the image and apply the lifting wave transform on it. And as we said, that we are going to use the same approximation band here, but we are going to make another division so we can have another version of it, which is smaller, so that it has less number of bits, so we can distribute it easily on the image. So now let's see explain how to get the bit planes. Now just keep in mind that we are going to apply the bit planes on this portion of the image. So if the image is 512 by 512, we are going to get the first approximation band to be 256. And if you applied it again, we are going to get, can we get the answer? 128, because we are defining. Okay, so now I want to hide a version of the image with the size 128 into the original image, which is it was in the beginning was 512. Okay, so now we need to hide this inside this. And to hide it, we said that we are going to go for bit planes that we are going to see here. Suppose that this is an instance of the approximation band, which is that one. And it has some pixels, and we see that the pixels are between 0 and 255 as a grayscale image that we are using. So I'm going to, if we have 165, it's consists of 8 bits. If we see that 0 to 255, it's 8 bits for each pixel. So I'm going to get the binary of this. First place is to convert this number, this pixel, to a binary. Then, this binary number, each bit of it, each bit of this binary is going to be applied and sent to one bit plane. What that means? That means I'm going to create a new bit plane with the same size of SS2. Get a bit plane with the same size SS2. If it was in this, and it says 4 by 4, so it will be 4 by 4. In our example, it is 128 by 128. So if I have it 1, so I'm going to get the first bit of that to be this plane. And another plane will have the second bit. And a third plane to have the third bit. Fourth for the fourth bit. You see that we are just taking this bits to be distributed to 8 bit planes, 8 binary bit planes. Okay. Accordingly, we are going to have for the other bit, which is the fifth here. Let's have another color. Which is this one. And for that one here. And then to this one. And finally to have that one. So now we divided this one to 8 bit planes. This is how to divide the binary image into 8 bit planes. By the way, these bit planes, if we are going to gather them together, we can get, of course, we return back the approximation band. And this is what we are going to do in the receiving side. So let's take another example for this. Let's have 129, which is this one. According to that, the first bits will go to the first plane. So the first bit, which is 1, will going to be here. So it will become 1. The second one, which is 0, to go to the second bit plane. The third will go to the third bit plane. The fourth, 1, 2, 3, 4. So it should be here, right here. And then we have another one here for the 0, and another 0 here for that one. And here we have this bit plane. And finally, we get this. So according to that, as much as we have space here, we're going to create bit planes for that. Now what we achieve, we have bit planes for each bit. Our duty is to hide this bit of plane, which is size is 128 by 128, is to hide them inside the original image, which is 512 by 512. Because we have limitation of size, we have, before we start, we have to make some calculation to see if our image is enough to hide them all or not. So because in our work we are using, in each 3 pixels we are hiding 1 bit only, so we should make some calculation to see how much, what's the maximum bit we can create. So in our case, if we have 512, let's say, let's go give this. let's have it as layout. What is the maximum size that we can save in our image? If we have it like this, our size of the image is 512 by 512. Okay, this is the size of the image. And then we are going to divide them by 3. The result will be the maximum payload that can be hid inside it. That means the maximum number of bits that can be hidden inside it. So if we have it, let's make a calculation. Why divided by 3? Because in each, it means just so in each one, sorry. Why we are dividing by 3? Dividing by 3 is for a reason, which is if I'm having 3 pixels, as we said, like that, and I want to hide the pixel in the middle one. So in each 3, I will just hide in one because this pixel will be changed to the average of the 2. And then this average of the 2 that we have, if we are going to add the bit plane value or to subtract it. According to that, in each 3 we are going to hide 1 pixel. Why is that? Because in the recovery, we are going to find the average again. And we check that one. Is it more than or equal? More than or less than the average? If it's more than the average, that means the original bit plane that was saved is was 1. Otherwise, it was 0. Okay, so according to that, I want maybe in the end, we can have some rest in the end of this this hour. Try to find out what's the maximum bit plane, and if we are using it, can we hide all the bits or not, and why? And I'm going to answer that after in the second part, inshallah. So after I make my bit planes according to this, the result will be like that. I have a grayscale image like this one. I will get 8 bit planes according to this. If you see that the most significant bit is the most important one, which has more features of the image, but the least significant bit is nothing more than noise. So that we can tell from this, if we don't have enough size for the image, it's not necessary to hide the least significant bit, or even the second least significant bit, or even the third. Less, and the rest depends on the details. Maybe I will not recover it 100% the same, but if I just get back my information, for example, the car plate number, so it should be good. Or I just get the face of the person, it's also be fine. So accordingly, we can decide which bit planes that we are going to hide. So this is the importance of bit planes and why we are using them. If there is any question, please tell me before I head to the MATLAB.
Any question from participant? Anybody
Okay,
know?
shall we continue? No question, right? Shall we continue?
Yes, I think you can continue, Doctor.
Okay. So I'm going to go back to the MATLAB, to the code that we have, and to explain it. Okay. First part is this one. First, we image read the original image that I have. And then we convert it to double because we are going to have calculation on it. So I'm going to apply the lifting wavelet transform. This is what we talked about yesterday, which is how to apply it in this case. So we specify which wave that we have, and then which and what are the divisions that we have. So according to this, we divide the image into S1 approximation band, which is the important one, which has the features of the image, and D1, S2, and D2. And then we are going to apply on S1, which is the most important one. We are going to apply another wavelength on S1 itself. Okay, another wavelength on S1 itself. So we are going to divide S1 in this case to SS2, DD2, SS3, and DD3. So we are going to have another 4 bands. Accordingly, the important part for us is the SS2 in this case. If I'm going to show now, let's say figure, let's have figure 7, let's say, image show S2. And you run it. I will go to the figure 7. If you see that this is the original image, let me also show the original image. Now with the first one, I'm showing the original one, and in figure 6, figure 7 will show the SS2. If we run that, this is the first, this is second. If you see that we want to hide this one inside this one. The difference in size is important. As we said that because we want to hide it in each 3 bits, we are going to hide 1 bit. And also here, each pixel consists of 8 bits. So we are going to hide 1 bit of this 8 inside this. Accordingly, we are going to hide the size of SS2 multiplied by 8. Okay, so and to get it inside this pixel of the original image. So this is the original one, and this is the next one. So now we got SS2, which is this one. We want to convert it to bit planes. This is the equation of how to extract bit planes from from one after one. What I want to do, let me just comment this to not have a lot of images. We have this operation for plane 1. Okay, I name it as P1. It's what? It's mod floor SS2 divided by 2. What we mean by this? If we apply this operation, okay, if we apply it, that means we want the modulation of dividing by 2. That means if the original image, for example, let's go to the calculator. So the calculator is working or not? Okay. I have, for example, 129, and the binary of it, the last bit is 1. Okay, so if the remainder of odd number, always it will be 1, so that means that bit is 1. If the number was odd, that means the first bit of the binary is 1. If the number is even, the last bit will be 0. This is a method that we can tell that this bit is 1 or 0. So what we are going to do, we are going to calculate the mod of the SS2 of the first bit, 1 after 1. Okay, so if that bit equals to 1, that means that the number is odd. If it is 0, that means it's even. So if I can get it from the even and odd if that bit is 1 and 0. And in the same time, in the same method, if it's clear, if I divided all the SS2 by 2 and then by 2, I'm going to get the second bit, because it's like taking the first one and then the second one. According to that, whenever I divide by 2, I go 1 step ahead and get just this bit, only the remainder of it. So By doing that, in all this, I'm going to get 8-bit planes from the least significant bit to the most significant bit. And now let's focus on figure 3 that's going to be shown. Let me just close all. Let's show, for example, P1 and run. This is P1, figure 3, that we are showing here. If you see, it's nothing more than just a noise because it is the least significant bit. If we go further to, let's say, plane 4, which is the fourth bit, as we see here that we said the fourth bit is more important, for example, this one. It has details more than this one. So if we go for that and run, we can see that we have a little bit details of that. If we go ahead and we get, for example, plane 8 and we run it, we can see that we have more details of the image, and mostly plane 7 will have the inverse of plane 8. See that this is plane 7. So according to that, we have 8-bit planes. Each bit planes, if you go to the MATLAB and read them, let's have here, we can read, if you are not using the MATLAB before, in the workspace, you can have all the values of the file that you get. For example, if we have P8, you see the values are either -1 or 1. By the way, I changed the 0 to be -1, so because we cannot to differentiate it between if we are either add or subtract, because we said that we have the average and we are going to add a value or subtract it. So we either multiply it by -1, add it by -1, or add to it 1, so that we can have the difference. If it is 0 and we add a 0 to the average, it will be nothing. I will not tell if this one was 1 or 0 in the first place. Accordingly, we have this bit planes, and then we change the slices to 1 and -1. We change slices to 1 and -1, as we said that if it is less than 1, so we are going to make it -1. That means if it's 0. Else, so we are going to keep it 1, so we don't need to write the else here. And then the next place after the bit plane, we change them to 1 dimension to continue. So now let me continue with that. If we have no questions, we change sizes to 1 and -1 to get the difference between them, and then to change the bit planes to 1D. So 1 dimension, that we are going to get all the bit planes together and hide them one after one. Next step is now is to distribute pixels to bit planes. What to do now? We got the bit planes, we got them as -1 and 1. Now it is the time to distribute them among pixels, among original image pixels. So what we are going to do? This is the original image. This is the original image. And suppose these 3 are pixels of it. I have an even pixel and odd pixel and another even pixel. The new odd pixel value, this one in the beginning, I'm going to change it to the average of the 2 that surrounding it. Even pixel 1 plus even pixel 2 divided by 2. So it will be the average. For example, if this one was 7, as we said yesterday, this one's 9. So this one, whatever its value was, for example, if it was, for example, 6, I'm going to change it to 8, to the average of the 2, 7 and 9. And then in the receiver, and then I get my bit plane that's going to be shared here. If it was -1, I'm going to add it, so it will be it will be 7. If it was +1, it will be 9. In the receiver side, when I got this image back, I'm going to have the same, these two. They are not going to be changed. They are going to still 7 and 9. I'm going to calculate the average. It will be 8. And then compare this 8 with this one. But now if the pixel is -1, the result is 7. So I have it 8, but the result I have 7. That means the original pixel that I have, it was minus, because 7 is 8 minus 1. So I can tell that this -1, it was 0, so we can get it back according to it. So the equation of distribution of P8 is like this. For I equal to, because I'm going to start from the second pixel and go 3 by 3. If you see that, the steps that I have 3 by 3, that means I'm going to have the 2, the second pixel, and then go to the 5th, because the 2 is surrounded by 1 and 3. And the 5th is surrounded by 4 and 6. And then if I go to another 3, it will be 8, because 8 is surrounded by 7 and 9. According to that, I'm going to go 3 by 3 for it. And then what I'm going to do, the average is what? I'm going to go to get the value of the image. I converted to 1D of I minus 1. That means if the I is 2, so I minus 1 is the 1, the pixel in the first position. And then I plus 1, which is the 3. Take the average of them. Okay, so average. And then add the value of the plane to the average. Add the value of the plane to the average. Now the question is why I'm using this 5 for multiplication. I'm going to answer this question in the second hour. We're going to have some rest for Dr. Zaid, maybe share the link for you for registration, and we're going to start for the next hour. See you till then. Thank you. Doctor, you can take the mic, please.
Okay, actually, I already shared the link for the attendance.
Okay, so we're going to have some time to register. If anybody have a question, and
Yes,
then
I would like to open for any question.
okay.
It is very interesting because you are very specific about this bits you hide. Okay, I think there's a raised hand from Dr. Dujan Taha there. Dr. Dujan, do you want to ask? Yes.
Yes.
Ask question?
Yes.
Yes.
Salam
Alaikum
alaikum.
salam.
Thank you for this excellent presentation, Doctor. Thank you for this session at all. I wonder how this procedure will differ in case of using colored images. What about calculating the maximum value we can embed in the original image? How to deal with the color frames RGB, as you know?
Thank you for your question, Dr. Dujan. If we are going to have RGB images, so that means we are going to have 3 cases, R, G, and B. So either we are going to manipulate each one of them as R and G and B as different images and apply for it, or we can change the image to YCBCR and take the luminosity part of it, which is also represents the luminance of these images to YCBCR, and make that change in the same way. And then we can retrieve the image back to colored one. And for the maximum the maximum embedding, it's we're going to talk about maybe in the next session, which is depends on the image itself. How can it tolerate noise? This number 5 that I talked about is the embedding strength. So it can be changed according to the image specification or the perceptual map that can be used, that how the eye can tolerate the noise in that cases. And thank you for the question.
Yes, Doctor. I'm asking about the equation that you presented before, which divided by 3.
For divided by 3.
Yes.
Yes. By the way, we can take, if we are going to YCBCR, it will be the same because I'm going to hide in just the
Yes,
luminance
yes.
one.
We will treat it as a gray level image.
Yes, it is the same, and the other parts I'm not going to take care of them. I'm going to leave them and just to take one part of the RGB image, white CBCR image, and then I'm going to make the change on that one.
Okay, Doctor. Thank you very much.
Most welcome, most welcome.
Thank you, Dr. Jan, for interesting question. Any more question from the audience? Dr. Taha, maybe you can show one of your slide on the coding. So
Yes, of course. I
the
just
previous,
draw a lot of things there, okay?
I think the one with code. Yes, this one.
This one, Doctor?
This is on the constructing part, right? No, the previous one.
Yeah, the one that we finished with, Victor. This one that you finished with. That one?
No, the code just now. Previous
Doctor
page.
Zaita, this one, you mean?
No, this one you want to explain about the embedding strength, right? No, previous one. On the coding part. Yes, I think this one. This one. This floor. This one is actually taken from this lifting right now. Just now, right? The SS2.
Yeah, the first part that we have is the lifting one. Here we have the
Okay.
first application of lifting with the transform, which converts the
Okay.
image, the original one, to 4 bands like this. And then,
Okay.
as we said, that
Okay.
this is the most important part of the image. Okay, so we are going to divide it again to 4 other parts
So let's say if we didn't
by
apply
using
this,
this one, this equation.
yes, the size with 1 to 8,
If
right?
we didn't
Okay, I just wondering if we didn't have the original image, is it possible to apply this code for the temper detection as well?
Yes, doctor. As you are going to see in the next part in the detection, it's blind. We are not going to depend on the original image because
Okay.
we are going to hide the image inside the original one itself, and we are going to distribute that one with the embedded pixels. So there will be an embedded pixels of the original one inside that image. And then when we are going to send it, it's going to be auto recovery by itself. It will not need the original one, of course.
So
Because the
maybe you
SS2
can,
itself that we're going to have, it will be hidden here.
Doctor, maybe you can explain a
So
bit further about the difference between blind recovery and then in general lah, not based on the code, but the difference between blind recovery and the normal, the one with which require reference image.
yes. For the difference between the two is that some algorithms need the original image and they compare the two together. For example, if you want to get to know if that image is altered or not, is it modified or not, you have to get the original one. That means you are the owner of the original image, and then you try you try to compare each pixel or have a way for comparison between the two. But in many cases, as I'm a user, I will just see an image inside in the internet. I don't have the original one from the photographer, for example. So how I get if it's the original one or not, if it's altered or not? So the best solution is to make it blind. That means it will not depend on the original image. Only the image that's sent via social media or via internet, or whatever the mean was, what it was, according to that, I'm going to get back the original data. So without having this, another advantage of using blind is that you are going to, as you said, that we have 3.2 billion image in the internet. That means if I want to have a recovery image which is not non-blind, I should save in the internet about 6.4 billion image for example, etc. images to be saved as a reference for me. So of course it will be waste of memory. That's why the blind presentation algorithms is much better than non-blind. Hopefully it was clear, Doctor.
Yes, yes, very clear. Thank you, Doctor. So,
Thank you. Okay, let's continue if there is no other questions.
yes, I think we can continue.
Now we stopped in this position where we distribute the pixels of the bit planes on the original one. What I will have here, I want to distribute the -1 and 1. As we said, we are going to find the average, and according to that average, we are either add the pixel if it was 0, if it was 1, because we have a binary pixel, or subtract it if it was -1. So what's the value that I'm going to add? If I just add 1 or -1, any change in the image, it will be very fragile, and it can eliminate that bit. So it's better to have a higher value to the embedding. So in our case, what we did, we multiply we said that it's either -1 or 1 for 0 and 1 for the binary. We multiplied them by 5. Why is that? To make the change more strict, to make it more robust, so that if I change that image and any attack applied to the image, it will have better toleration to that one, because it will be more than or less than by 5 values, not 1 value. However, the number 5 here is constant. As we are going to talk about future work, this 5, it can be changed according to the feature of the image in a certain region. For example, if the change was applied in a textured images, it will not be like when I have a sky. If I have a change inside the mountain surface, it will not be like the sky. A simple example that we can say that if it's easy to see a bird in a sky, but it's difficult to recognize it if it's on the tree, because the texture of tree leaves is more than the texture of the sky. According to that, this 5 will be changed for our next work to be depends on the perceptual map. It will not be a fixed one. So now let's talk about extracting process. I will just go back to that slides that we go for extracting. Now I received an image and I shared it in the internet using I saved the image, the original one, and this original image having the pixels hidden inside it of the SS2 of all of it. Now I want to extract that one. I want to extract it. What I will do, first I read the image which has the bit planes inside it. We apply the LWT again, the decomposition again. So now we are applying it to what? We are applying it to the image that can be tampered. Okay, so I will have that, let's say it's tampered. I will have the tampered SS2. Tampered SS2. Then I'm going to go through all the pixels to return back what? To return the original SS2 that I have hidden inside the pixels of the image. So now I will have two SS2, the real one and the tampered one. Then I'm going to compare this approximation band with this one, pixel by pixel, or group of pixels by group of pixels. If there is a change, that means this pixel or this group of pixels have been changed. What I will do, I'm going to replace the original one, the faked one, with that one. I'm going to take them and return them back. A question may be raised here. Why I'm not just taking all SS2, okay, the retrieved one, why I'm just replacing a part which is modified? The answer is that the SS2 that I hidden inside the image, it's not the original one, because I said that we have 8 bits. I'm going to answer that question. If I have 8 bits, I will not hide all the bit planes of the 8 bits, because we said that the last least significant bits are not that important of the features. So I don't need, I will not be able for the size of the image to hide them all. I'm going to hide, for example, 5 bit planes only, not all of them. Accordingly, the SS2, if it is not changed, let me keep the original one that's not altered in that tampered SS2. But if it's tampered, I'm going to make that change and change it back. So according to this, after I apply it, I'm going to replace the retrieved approximation band and apply the inverse lifting wavelet transform with what? I have it here as I applied it, but this one will be the original SS2 if there is any change. So when I'm going to apply the inverse of lifting wavelet transform, I'm going to get back my image. I'm going to get back my image after alteration. So let's talk about, sorry, let's go back for this because we passed this. Okay, how to apply this on MATLAB is by the following. Now I'm going to make a for loop because we said it's one dimensional, so we change the image 128 by 28. I will do what? I will take the average again. Okay, so finding the average to return the value of binary. As we did in the embedding or distributing step, we found the average. So now we are going to get the average back. And what we are going to do, we found the average of I minus 1 with I plus 1. That means, as we said, that if I is 2, so we are going, if I have 3 pixels, 2, 1, and 3, I minus 1 is the 1. Let's say that it has a value, as we said, 7. And the 3 is the value is 9. Well, let's make them 17 and 19, let's say, have bigger values. And we are going to find the average. The average of this is, we have 18 as average for them, 25, 36, 18. Sorry. If that 18, and I get the image here, the pixel of the plane, the ID of I minus 1, 17, I plus 1, 19. I'm going to get this value. If it was, for example, let's say it's 20. Okay, in our case, if we are using 5, it will be either 23 or 13. Either 23 or 13, because you are using embedding strength as 5. So if it was 23, that means the original bit is 1. If it was 13, that means the original bit is 1. Even if it was not 23, if so suppose that we have some attack on the image and this one it became, for example, 21, it's still more than 18, so I'm going to consider it as 1. So the difference between them, I, which is this one, with the average, it will give me the returned plane of that one. If it's more than 0, so it will be 1. Otherwise, it will consider it as 0. Bit by bit, I'm going to return back all the bit planes. Then, as I converted them from 2 dimensions to 1 dimension, I'm going to return them back to 2 dimension, and we are going to get one after one for all that images. Let's talk about the results that we obtain from this algorithm. First, we have two parts of results that we want to discuss. First, after changing the middle value, is the image still good, has a good appearance? Is it distorted or not? Because as you know that I didn't send the same image, I changed some value of the image. I sent all the values in the middle. So how it will appear? So this is, we check the image quality, okay? And then we have another check, which is the information can be retrieved correctly if I make some tamper on it or not. So for the first one, which is the image quality, we have two values. The first, the PSNR for peak signal to noise ratio, and the structure similarity index, SSIM. The first one is a quantitative measure that's used to compare the original image with the image that I distribute the approximation band inside it. So it just have the difference between the original image, which is this one, and then the tampered image. I mean, this is the original and this is after the distribution. It is not the tampered, it's the image after distribution, after I hide the data inside it. So according to these two that I have, I will just make a summation to check them one after one, and then divide them by the m multiplied by n, which is the coordinates of the image. And then to find the logarithm of MAC, which is I found it here. And I will get a value. The value of PSNR, if it's more than 30, some references more than 25, it will be good. However, PSNR is not considering the human bias in observing noise, because the human eye, as we said, that it has different evaluation for different type of noise, if that noise is applied to different types of image. So according to that, it will consider the change in the sky as the change in the mountain surface. So it's not realistic. We need another and better one, which is the structure similarity index, which is take more the human vision system and the structure of the image into consideration. So according to that, we are going to use the structure similarity index as another metric that's going to find it. So we are going to use both and see the results. These are images that are used for our comparison and for our results. And we hide the data inside these images. Images are mapped from image 1 to image 9. So image 8, sorry. Okay, so image 1, 2, 3, 4, 5. So I'm missing image 1. So this one, image 2, image 3, 4, 5, 6, 7, and 8. So what are the results that we obtain in that? If we see that the PSNR for images are, as you see here in that one. Okay, these are the PSNR, and the average is 31 for these random images. And for the SSIM, if you see that when in SSIM, all the values are more than 0.95. And according to references, if the images are SSIM more than 95, that means they have no big change. So these values are very accepted, and they denote that the image has no big alteration, and it is very accepted values. Now this is the first evaluation. We know that this image is not distorted, so we can distribute them. If we distribute them and we apply the data after some attacks. These are some attacks that we applied for the image. For example, in this image, we change part of the the number of the car. And if you see in the retrieving, we can get it back. Here we take a part of the face and we retrieve it. Here we get the man and we retrieve it. And here the face of the cameraman, and also it can be retrieved. Here we have another part of images. And these are the results. If we see, we could retrieve the image back, but maybe the quality is not exactly the same as the original one, but we can take advantage of, as we said, from the original images so that we can get the unchanged areas first. Second, this method is using just one instance of the bit planes. So as we are going to see in the future work, if we use more than one instance, the results will become much more better. So how to enhance the, before I go to image enhancement, let me just apply this code in MATLAB. I want to run this. The last part, we run this one. Let's go to run this. I want to run this plane. So if you see that, I want to find the average. And this is what I explained, how to find the average and distribute it. This is the number 5 that I embed the image inside it. If you see that, we have the image, and that's one. If I make the 5 here as a more embedding strength as 500, let's say it's very extreme value, but let's try it. If you see this part, these are the pixels that are changed in the image. And we're making 500, even it's integer, we have to 500 maximum. The image value here affects that one. So depends on the type of the image, okay? These values can appear or not. So we can tell that from this part, the middle plane or the first plane is hidden inside this one. Let me change for the second one. I'll make it about 50. If you see, I don't know if it's clear on the presentation, Doctor.
Yes, it's clear.
Okay, now this is 500 and this is 50. If you see, the effect is less. Whenever we have higher values of embedding strength, it will affect the image. But in the receiving side, it will give us better data in the retrieving. It will be more robust. So this is the trade-off between the two. So one after one and so on. I will go to the code again. I will go to the extract process. If you see that, let me go take the image one. I will go to just check for the first image. If we see that in the block, we try to just block that part of the image, this one, and here we can get it back. Just a minute. Now we have this number, which does not appear, but now it's clear that it was 8272. This is the how to apply it, and this is the code for distributing, for the extracting that process back. Accordingly, if you go back to our slides, how these results can be enhanced, it can be enhanced by the following. First, if we are using multiple copies of each bit, that means the bit planes, before I distribute them, I divide them more. But we need to know the size of it, as we said. So if we have, for our size of the image, let's make the calculation. If we have 512 by 512 divided by 3. So let's see what is the maximum size that we can save. I will go to the scientific one. 512 by 512 divided by 3. So we can hide 87,000 pixels. This is the size that we can hide, 87,000 pixels that we can hide inside them. That means this number of bits that we can say. But according to our image that we have, if how many bit planes that we get? We have the following, how many bit planes? We have 8. Okay, so if we have 8 bit planes, and each bit plane is consists of 8 bits, and the size of one bit plane is 128, so it equal, we said that this one was equal about 87,000 something, 181. So let's try to calculate this. I'll keep this back. So we have 8 by 8 by 128. So it will be 8,192. So this is just how many pixels that we have for this. So according to the number that we get, we can specify how many bits that we can find for each one of them. So another part is to use perceptual maps. That means we are going to consider the human eye, and finally to get the region of interests of that. If we have, we don't want to hide all the image, we want to hide just a part of the image, we are going to get the result. We are not going to hide all of it. For example, instead of adding all of it and hide it all, we care about the number of the plates, so we can just hide this part of the image and distribute it, so we can have many distributions and we can have multiple copies of it. That's all for me for this, and I explained what's perceptual map. Thank you for your listening, and if you have any questions, you can ask.
I would like to open the session for question. Any question from the audience? If not, maybe I can ask few questions, Doctor. Let's have you, Dr. Taha.
Yeah, Doctor. By the way, just I want to mention before, we have to multiply this one 128 again, so we can get this number. I just want to clarify this. If I have the size of this, what should this pen? Okay, this multiplied by 128. So this is the size of the band. If we see that 128 by 128 by 8 by 8, if you see the number that's going to have, it will be more than this one, as we're going to say. So it's not enough to hide all the 8 of bit planes. Okay, so we are going to find some region of the bit planes. For example, we're going to hide 5 of them only. Whatever the number that we're going to calculate, this will be suitable to hide inside this payload, the available payload of that image. If you are using bigger images, for example, 1024 by 1024, we are going to have better result for that. Yes, Doctor, please.
So this is you are showing the maximum number that we can hide, and as well as why you choose this now, is it?
Yes. Why we have these 5 bit planes, not all of them. Now, if you are asked to make some calculations, if anyone want to try to calculate it, they are going to find that the maximum bit planes that can be used in this instance is 5.
But this now, is it use 5 or 3? I think is it 3.
Now I'm using 5 bit. No, 5 bit planes. Yes, the 3 is the number. The 3 that we are using is that because we have each 3 bits, we can hide 1 in the middle of them. That's why. I'm talking about the original image. We can have 5 by 12 by hand, 5 by 12 by divide by 3. Why by 3? Because I'm finding for each 3 bits, I'm finding the average of the middle one and then change it. So I'm not changing all the pixels of the original one. I'm just changing one in each three. That's why the number of bits that are available to hold the data that I have is 500 by 12 by 500 by 12 divided by 3.
Very clear. But my question is actually totally different. I'm
Yeah.
just wondering because the result that you have is based on the square region less than 50%. If um, the template is more than 50% of the size of the image, um, does it able to get the image back? Have you tried that?
If we change, Doctor, you mean the size of the data that's going to be embed?
No, not the size of the data because this you have explained on this. What I mean is on the template result. Just now you show the image with the black box just now.
Let me go
What
just go
if
to the slide, Doctor, so that I can get your point. Just a minute. You mean this slide? Which one?
the black? Okay, maybe this one. Yes, any of this would be okay.
Okay,
Uh,
that's one.
so the black box is I think less
Yes.
than 50% from the image size. Let's
Yeah,
say
Doctor.
if
Yes,
it
yes.
has
I got the question.
larger
Yeah,
box, yes, what will happen?
okay. Doctor, the size of the box, if you see, it's different from one image to another. And
Yes,
what's
yes,
the
that's true.
important is that first thing, we can distribute the image pixel, the hidden pixels, on all of the image. Okay, so that if a certain portion is affected, the others will recover. If the image, the blocking part was touching the same place that were hidden inside the image, of course it will be
Mm-hmm.
affected. That means suppose that
Mm,
I hide the data of the face in the place of the face itself, okay? And the one come and block it, of course it will be affected. But if I had it in another place, it will not be. So, and also another thing, how many copies do I have? That's why I said that if we are going to have multiple copies of the band, it will be better for us. That means for me, I prefer that I'm going to hide 5-bit planes 3 times better than hiding all bit planes twice.
mhm.
Because if I hide one will recover the other. But if I'm going to hide two and one eliminate the other, it will be a problem for that. Maybe you are not going to guess which is the true one. So according to that, it depends on how many copies that I have and where the modification will be.
Okay. Thank you for the explanation. Anyone want to ask more question? We still have more time here.
Yeah. And by the way, Doctor, now in our new lecture, the way paper that we are going to discuss, inshallah, later, we are going to have a perceptual map and bigger images. The result that we obtained is better than this one, because we use the perceptual map, we use the high intensity of embedding according to the texture map. So it has, for example, in cameraman, we can hide in more intensity in the ground more than the sky in this place, or here we have in the flowers or any other image. So the result is better than that one.
To add this perceptual mapping, right? Perceptual mapping is not included in this workshop, right?
Yeah. We are going to maybe if we have inshallah next
Another
one,
series
we are
lah.
going to we are going to have to talk about perceptual mapping and how to create them, how to simulate the human eye as well, inshallah.
Okay, very interesting, Doctor. Um,
Yeah.
if maybe let's give some time for the audience to think about whether they want to have question or not. But in the meantime, is it okay if I ask everyone to turn on their cameras so we can take one picture for the second day because we need it for the reporter. Everyone turn on the camera for a while. Okay, I've seen is it Mr.
Yeah, I
Ravi?
will stop
Okay.
the presentation so you can take the image picture.
Okay, wait. I will change the layout. I think okay. Okay, anybody want to turn on camera? Anyone more? Right now we have okay, 1, 2, 3, 4, 5. Dr. Dujan. Okay, wait. Okay. Right now we have 5. Okay. 1, 2, 3. Okay. Okay. Because I do print screen, so I need to see it before I lose it.
Yeah.
Anybody want to turn on the camera? Anyone? Okay. Let's have another one. Okay. Okay, smile. 1, 2, 3. Okay, thank you. Okay.
Thank you, Doctor. And by the way, I want to mention yesterday we had a question about the dentistry. I'm not sure, Doctor, if you didn't get any images for dental. So if you still have, if you want to ask about that, we can communicate later. It was a question about how to affect the image processing in dentistry. We asked about what are the images that you are using and you want to enhance. But as general one, we can say that it is image enhancement can be used in a lot of fields. One of them is the image industry. And also we say that maybe we have a classification for the type of filling on the type of and the type of the teeth and the color of them. Many of that, for example, the matching the colors of the teeth and all of that. So if we have something like that, we are if you are having suggestions for future work, for future workshops. So just shop and thank you from University of Malaysia Perlis for helping for making this, and for Tishk International University, University of Mosul, and Sam Higginbottom. Yesterday we had Dr. Jiberson with us. That he apologized today. He has some urgent work that he didn't come. Maybe Dr. Miss Jiberson was coming with us today and she left. I'm not sure about the participants. But thank you for all of you, and it's a pleasure that we have this workshop with you all.
Thank you, Dr. Taha, for the words just now. Okay.
Okay,
I think
Dr.
yes, we have
I can't hear you
sure,
well.
yes.
Doctor, yes. Yesterday I asked you if you are going to send us some images of dentistry, and if there are some issues in that thing, so we can talk about them, talk how to enhance them, or how we can make applications for that reason. So if you still
yes, Doctor,
interested
I
in that,
ask you. Thank you so much
yeah.
for reminding.
Okay.
Yes, actually, I searched a lot, but there is just companies that concern about CAD cam, about intraoral camera. That I can find. So inshallah, I will come and let's discuss about this.
Inshallah,
I couldn't
anytime you're
find
welcome.
any article, any scientific article. I just see companies. That's it. So maybe I can communicate with my professor to supply me with these. Then I will send you an email.
Yes, it's great. Even just it's just taken by companies that if you are going to do something and make it public, it will be a good point. That means it will be something new. So it should be a motivation. Actually, maybe it's difficult,
Inshallah.
right? But show the motivation. Thank you, Doctor.
Thank you so much, Doctor.
Okay, I will include Dr. Taha email in the chat. Wait,
Okay.
Okay, so if anybody want to ask further question about this workshop or anything related to image processing, just email Dr. Taha. You can CC as well to me. I think you got my email through the invitation previously, so you can use the same email address to send some question related to image processing as well as MATLAB as well. Okay, I really appreciate those all the participants who attend for the second session today. Do not forget to fill in the attendance form, so that is I will need it for the purpose of record. Thank you for spending your time, and as well as I would like to thank you, Dr. Taha, for his effort and his time spent to prepare for the workshop. I hope this is will be give benefit not just to the participant as well as um, to us lah, to University Malaysia Perlis and to IU, since we have this as a start as for collaboration. So thank you again. I would like to open if there is any feedback from the audience and as well as from Dr. Taha maybe on.
I just thought would like to thank you all and thank you all Dr. Rosalita for your work again, for your efforts, and for all your comments, Dr. Dujaz, I see, Dr. Sura, Dr. Azamuddin, Siti Khadija, Muhammad, Mr. Dr. Muhammad Anwar, and all of you. Thank you for your attendance and thank you for being with us in this workshop. Hopefully we're going to have more in the future. Thanks a lot. Thank you very much.
Please, the current response right now for the form is 13. So if anybody is missing, just send let me know so I can send the link for them to fill in. Please provide the feedback lah. So maybe we can arrange another series, maybe not on another topic on, but related to the image processing as well lah. Okay. So I
Yeah, we
think
can
that's all.
give you suggestions. You can say to Dr. Zalita or to us if you have suggestions about certain topics, so we can work on that specialized sessions for this. Inshallah.
Okay, thank you, Doctor. So I think that's all for today. We finished earlier than the time that we have. Okay, I saw Dr. Hamid. Do you want to share any opinion? Hamid Muhammad? No? If not, that's okay. So I think that's all for today. So thank you, everyone. Have a nice day. Take care of your health.